dx. All right, so what were your thoughts on this when you first got it?
I tried change it to 1 minus cosine x squared minus 1 plus cosine x squared.
Okay, so you're working on maybe working with a trig identity?
Right.
Okay, so looking at this right away, I don't have an antiderivative for tangent squared x, and the u sub might or might not work right away. So I might ask, okay, is there a trig identity? And that's what you would look at, was maybe some trig identities. Okay, so what I'd like you to do right now is I'd like you to think in your head, okay, what trig identities do I know that involve a tangent squared x? Right? No, wait, hold on. Turn to your neighbor. Tell your neighbor what's in your brain.
Which is this. Squared x.
Oh, so this is saying that cosine squared theta is equal to 1 plus cosine theta.
That's this one right here.
Yes, that's just saying, this is my thought bubble, that's what I'm
I
going
got stuck on 15 and 9. Yeah. Yep.
All right. Anybody have a neighbor who came up with a trig identity involving tangent squared? Anybody at all?
My neighbor did.
Your neighbor did? What did your neighbor say?
That 1 plus tangent squared equals secant squared.
Plus tangent squared equals secant squared x. Okay. Anybody come up with anything different?
Sine squared x over cosine squared x.
Okay, so tangent squared x is equal to sine squared x over cosine squared x. Any other? Okay, so we have these two trig identities, and so things that we might think about is this first one up here. If I rewrite that, then I have tangent squared x is equal to secant squared x minus 1. And so these are both options for substituting in for tangent squared. So I could either look at sine squared x over cosine squared x, or I could look at secant squared x minus 1. And so I might think to myself, okay, do I know some antiderivatives? This top one up here, I'm not really sure what I might do with that one. But the bottom one, antiderivative of 1 is easy. And do we know an antiderivative for secant squared? Yeah, we do. We know, so antiderivative of secant squared is tangent x. Derivative of tangent is secant squared. So I can replace my tangent squared with secant squared x minus 1. And now both of these guys are known integrals or known antiderivatives, and we have tangent x minus x plus c. All right, any questions about that one? So that one will totally stump you unless you can replace with the Pythagorean identity for tangent squared. Okay. Questions or comments? Yes?
Can you go over 17?
Number 17? Okay, so number 17. You're getting Nick, right? Okay, great. So in 17 we have the integral of secant squared x times tangent x dx. And Nick, what did you try on this problem? Start out.
Well, the first time I tried substituting u for secant x.
Okay, so you tried, okay, u is equal to secant x. This seems like an absolutely reasonable idea, because if I rewrite this, I have secant of x quantity squared times tangent x dx. And so choosing the u to be the inside function, great rule of thumb, so let's see what happens. So we have du over dx is secant x times tangent x, which means that dx is equal to du over secant x tangent x. Okay? So we go back over to our integral, and just sort of continuing to work with it the way we've been working with these, I have the integral of u squared times tangent x. and my dx is du over secant x tangent x. Okay? Not bad. I can certainly cancel the tangent x's. But I'm sad because I still have an x involved with the secant x down here, and so things are not looking so good right now.
Can you replace it with the u? Because u equals secant x?
Okay, so here this secant x, not really sure what to do with it, but then remember that u is equal to secant x. So let's replace that secant x with a u. So we have the integral of u squared times du over u. And now life is good, because now I can do some canceling. And I have the integral of u du. All right. Nick, does that help you on your way?
Oh, well, that's what I got, but, did it turn out the, answer was tangent, tangent squared x? Because I took the antiderivative of that, asking was u squared.
Okay, so here we go. We've got this is equal to 1/2 u squared plus c, and so that is 1/2 of secant squared x plus c. So a legitimate final answer. And in the back of the book you said gave you something different.
Yeah, it was 1/2 tangent squared x.
1/2 tangent squared x was their final answer. Okay, so here's the issue. The issue is that we have two totally different looking final answers. Ben, you have a thought?
Yeah, so tangent squared x is equal to secant squared x plus 1. Or secant squared x minus 1.
Minus, yeah.
And that minus 1 might get eaten by the c, right? So that they're always equal to each
So
other.
1/2 secant squared x minus 1/2. So 1/2 tangent squared x is equal to this guy, which looks just like what you have, and that exactly that negative, that minus 1/2 is part of the constant. So these two answers differ by a constant. So they're still both valid final answers.
So
So you wouldn't have to.
what's the answer? Just
Well,
u
so
here?
this would still, so in this answer, the plus c gets the minus 1/2 munched into that.
How'd you get that from?
So why does the book have this other answer? Well, there's an alternate option for the u up here. You could also choose u to be equal to tangent of x, in which case derivative of tangent is secant squared, and so that would also cancel things as well. So either choice for u actually works in this particular example. All right, other questions or comments?
So u du is the answer? And then you just plug in secant x?
So once I get to here, I take my antiderivative,
Oh, okay.
and so here's my antiderivative, and then I plug back into my u. Okay. Questions or comments on this? Nick, does that answer your question? Great. Okay, so I'd like to wrap up this section 6.2 material about interesting trig u subs, and in particular I'd like to highlight two important antiderivatives that are ones you want to add to your list of known integrals. So as of Monday, we talked about, so let's title this 6.2 continued, new integrals that we have or know, or will know, that we find via clever trigonometry, identities, and u subs. Alright, so the one that we talked about last time was the antiderivative of tangent x, and that is equal to the natural log of the absolute value of secant x. So this is one that you now have. You should add it to your list of known antiderivatives, post it on your refrigerator, tell your friends about it when you're hanging out with them on a Thursday night. Hey, I just found out this new antiderivative. It's pretty cool. Here it is, and I can even show you how to find this antiderivative if I forget the formula. There's two more like this that I'd like to talk about. So the one that I'd like to talk about is related to the antiderivative of 1 over 1 plus x squared. Alright, so 1 over 1 plus x squared, or 1 over x squared plus 1, it doesn't matter really which order you look at. That's the derivative of which function?
Inverse tangent.
Yeah, arctangent. So the antiderivative of 1 over 1 plus x squared is arctangent x plus c. And so if ever you are walking down the street and out from the dark alley jumps the integral of 1 over 1 plus x squared dx, you immediately have tools to deal with that. You say, ha! The integral of 1 over 1 plus x squared is arctangent x.
Plus C.
Plus c, thank you. Almost lost that word. Okay, so that's great. Now, the next problem is you might be in a different state or a different city, and you come upon a new dark alley, and out from that dark alley pops 1 over 16 plus x squared dx, the integral of 1 over 16 plus x squared dx. And you say, oh, I know you, or at least I know your family. I know your family, I know all about you, okay? And I know that you're really closely related to this 1 over 1 plus x squared, but you're not exactly the same. Okay. So how do I deal with you? All right, well, when I look at this, my immediate thought is 1 over 1 plus x squared. Can I take this guy and morph it and form it into something that looks similar to this guy over here? Now, what might happen is variables might change, but I want to make this guy look like, we want this to look like the integral of 1 over 1 plus maybe some other variable squared, maybe I'll call that u, du. So I need to get a 1, that is the most important piece. I need a 1 in that denominator. Okay, right now I have a 16. Ryan, you have a thought?
My question would be, it would be wrong to pull out a 1/16 and put it in front of the integral sign.
Okay, so let's think carefully about how that might happen. If I want to pull out a 1/16 and pull it into the front of the integral sign, maybe what I'm doing then is factoring a 16 out of the entire denominator.
Oh, okay.
X squared.
All right, so let's see what happens if we do that. Just let's go ahead and explore that. That would give us a 1 right here in the first term. The second term, Mike?
I was gonna say,
So good question about the natural log. Natural log is not going to work because of the squared portion of, on the x. Okay. So if we just had 1 plus x in the denominator, we could think about natural log. All right. Let's look at this a little further. So if I factor out a 16, I get a 1. And if I factor out a 16, if I divide 16 out of x squared, I get x squared over 16. Okay, well we've kind of traded here. We've traded that we now have a 1 in our first place, but we have something not so pretty in where the x squared was. Alright, I'm willing to go with that. So 1 over 16, I can pull that to the front. And then I have the integral of 1 over 1 plus x squared over 16 dx. Alright. So looking at this integral that I have here now, I'm trying to make it look like 1 over 1 plus something squared. Is there a way to rewrite x squared over 16 as something squared? Okay, well, what would your u be? Okay, so,
X over 4.
okay, so yeah, I want this whole term to be something squared. So notice the bottom of 16 is really 4 squared. So another way to write x squared over 16 is as x squared over 4 squared, which I can write as x over 4 the quantity squared. Well, this is kind of cool. So one last way that we'll rewrite this integral is 1 over 16 times the integral of 1 over 1 plus x over 4, the quantity squared, dx. And so at this point, we have written our integral in this form, this 1 over, let me try that one more time. 1 over 1 plus stuff squared. Now that stuff that's squared is x over 4. So let's make this adjustment now. Let's let this x over 4 be our u. So u will be x over 4, which, by the way, is the same as 1/4 x. And so our derivative, du over dx, is 1/4, which tells us that dx is equal to 4 times du. Alright, so important information here. We have 1/16 times the integral of 1 over 1 plus u squared times 4 du. Alright, this looks an awful lot like 1 over 1 plus u squared du, with the exception of that 4, but that 4 we can bring out in front. And so we have 4/16, also known as 1/4, the integral of 1 over 1 plus u squared du. So now, this is really cool, right? I mean, we were walking down this dark alley in an unknown city, in an unknown state, and out jumps this integral that looks an awful lot like one that we know about, but not exactly the same. It's a family member. But we had to morph this guy. We had to change it and tweak it a little bit so that we can rewrite it so that it looks just like the member of the family that we know. Now we can take our antiderivative. So 4 over 16, that's 1/4. And then we have arctangent of u plus c. And so our final step is to replace that u, and we end up with 1/4 times the arctangent of x over 4 plus c, final answer.
Nice.
Okay, so thinking about this idea can actually work all over the place. This 16, there was nothing special about 16. You can throw any number in there that you want. In particular, you could rethink this as the integral of 1 over any number squared plus x squared dx. So 1 over a squared plus x squared dx. And think about that for this form up here. Up here, this was like writing 1 over 4 squared plus x squared, so our a value is 4. And take a look at what our final answer was. Our final answer was 1 over that a value, arctangent of x over that same a value. And so that's actually going to work every single time. You can even, if you're not convinced of it, you could actually start by writing 1 over a squared plus x squared and do the same type of problem that we just worked through here with the 16. So in the end, the new known integral that we have is the integral of 1 over a squared plus x squared dx is equal to 1 over a times the arctangent of x over a, and then plus c. And so this is our second integral to add to our list of known antiderivatives. Now, again, yes?
If a wasn't a number squared, would it still work?
It would. So let's say that we had the integral of 1 over 7 plus x squared dx. You could always write a 7 as square root of 7 squared, in which case your a would be square root of 7. It wouldn't be pretty, but it would still work. The beauty of both of these antiderivatives is that you can just memorize these, but if it comes up that you're out on the street and you blank on the antiderivative, you can always massage this and come up with the antiderivative just like we did on the board over here. So you don't need to memorize this, but it's helpful because it saves time, okay? But it's not required. Okay. Okay, so I'd like to wrap up with one final integral before we take our break, and this is the antiderivative of secant x. And this particular antiderivative is only mildly cool. And the reason this is only mildly cool is because what we're going to do here to get the antiderivative for secant x is a one-trick pony. Works in this example, it's kind of cool, but you're not going to use this trick very often, if ever again. So check this out. I want to know what the antiderivative of secant x is. I can look it up in the back of the book, or I can look it up in a table, or here's our one-trick pony. We're going to multiply secant x by 1. So we're going to multiply by 1, which I'm going to write in the form secant x plus tangent x over secant x plus tangent x. Totally legitimate thing to do because I am multiplying by a value of 1. The top and the bottom are exactly the same. Let's see what happens. We have the integral of secant x times secant x plus tangent x over secant x plus tangent x, and then I've got a dx at the end. Okay, so I have not changed the value of my integral whatsoever because I'm multiplying by 1. Alright, so this is secant x over 1. I can multiply across the top and across the bottom, and so I end up with secant squared x plus secant x tangent x divided by secant x plus tangent x, and then a dx at the end. Alright. So when you're done writing this integral down, take a close look at it. Take a look at the top. Take a look at the bottom. If you look at the top, for example, and take its derivative in your head, do you get the bottom? Or vice versa? Thinking about derivatives. When I look at that denominator, derivative of secant x is secant x tangent x. Derivative of tangent is secant squared. So the derivative of my bottom is exactly what's on the top, which tells me that this is a really good candidate for a U substitution. So somebody was absolutely positively clever in their choice of multiplying by 1, and it gave us a really cool opportunity here. We can let u be equal to secant x plus tangent x. Our derivative, du over dx, becomes secant x tangent x plus secant squared x, which tells me that my dx is equal to du over secant x tangent x plus secant squared x. And now I can make some substitutions. We've got the antiderivative of secant squared x plus secant x tangent x divided by u times du over secant x tangent x plus secant squared x. Who would have thought it? Who would have thought that all of this stuff could cancel just by multiplying by 1 in a funny looking way? Alright, our numerator cancels with the denominator under the du, and we are left with the integral of 1 over u du. And know all about that one. That guy right there, ln of u. ln of the absolute value of u plus c. So we end up with the natural log of the absolute value of our u, which was secant x plus tangent x. Alright, so our final integral in our list here of known antiderivatives that you want to add to your list and be comfortable with is that the antiderivative of secant x dx is equal to the natural log of the absolute value of secant x plus tangent x plus c. Alright, so add these three to your list, and then take a 10-minute break. Thank you for listening.